Hey everyone, welcome back. We're going to be working on this problem for discussion 21 from the worksheet. We are given a position vector, and we are asked to find the magnitude of the angular momentum at t is equal to 5 seconds. So we can write this way. So, okay, what is the identity of angular momentum? Well, the basic identity is r cross p. So your position vector crossed with your standard momentum vector. Okay, here's our position vector, right? So what is in momentum? Well, that's m times velocity vector. So now we need to find the velocity vector from the position vector. So dr dt is equal to 4t I hat plus 6t minus 5 j hat. Okay, so now we have this cross m dr dt, right? So we're also told that the mass is 2 kilograms. So that means we want to do our cross product, right? So let's do that here. Let's give ourselves a little room. So it's I, j, k. And I hat direction we have 2t squared. This is r, right? This is r cross p is going to be down here. Put that there, yeah. Here. Let's pull this down here so we know this when we need it. Okay, so let's see, t minus 5, 2 squared, 0 in the k hat direction, right? Now we have 2 times, remember we have to put, this is mv, right? Because this is r cross p, which is what we're doing down here, r cross p, and p is mass times velocity vector. Here's our velocity vector, right? So we have to do m, which is 2 kilograms, times that. So instead of 4t, it's going to be 8t I hat plus 12t t minus 5, 0. Okay, so we take the determinant. We take the cross product. Okay, and then we end up with 2t squared times 12t minus 5 minus, oh, I'm kind of skipping a couple steps. So here, if we look at I hat here, if we wanted to find the I hat direction, we have this times this, right? Minus this times this. That's just going to give us 0 in both. So I just kind of skip that. So this times this minus this times this, those are both going to be 0 in I hat direction. And similarly, for the j hat direction, we have this times this minus this times this. Also both 0. So we have nothing in the I or j hat direction. This is only going to be in the k hat direction, right? So now we have this times this, which is what I wrote down, minus this times this. So 8t times 3t minus 5 squared, right? So before we do a whole bunch of simplifying and algebra and stuff, let's remember what we're trying to find, and that is we want to know what angular momentum is at t equals 5 seconds. So we really don't need to go through the rest of this calculation. We can just plug in t equals 5 into both of these. And here, well, this will give you 25 times 2 times all of this. But this actually is going to be 0, right? T equals 5 minus 5, t equals 5 minus 5. Those are both 0. So our angular momentum, by the way, this is k hat. Our angular momentum is 0 all around. 0 all around. Okay, so the next question then says, when the magnitude of the angular momentum is 0, the magnitude of the torque about the origin acting on the particle at the same instant in Newton meters is. So now we have to find the torque. That's pretty much what it's saying here. Okay. Not too bad. Let's do the next calculation then. So what is torque? Torque is R cross F. If you remember from the last video that we did on this. Okay, so now we have vectors that we can take the cross product of. We don't have force yet, but all we have to do, what is force, right? So this is going to be your R position vector crossed with your mass again, times the second derivative of your position vector, right? This is R cross MA. Okay, so all we got to do is take the dv dt, which we found a minute ago. Excuse me. We found v a minute ago. Take dv dt of that, and that's going to give us... Let's just copy this here so we can actually see it. Right. Just doing a little rearranging here real quick so I can better explain what I'm doing. Okay, so that's going to give you 4 in the I hat direction plus 6 in the j hat direction. Okay, this is acceleration, so we're going to have a meters per second squared is going to be our units. You just remember that. Okay, so now we have our acceleration vector. We can just plug it in directly to our torque equation, right? Torque is equal to R cross MA. All right, so torque is equal to, we need our position vector. Well, let's just do this again. I'm going to take this and just rewrite it down here. This was for velocity, but I'm going to change this because I'm keeping the position vector, right? So now we have for cross M acceleration. So this is R, acceleration is going down here, M times acceleration is going down here. Recall that M is 2, right? So we have 8 I hat and 12 j hat. Okay. And then again, we just take, well, if we look here, so in the I hat direction, this is 0, this is 0. In the j hat direction, this is 0, this is 0. In the k hat direction, this is non-zero, this is non-zero. Okay, so we need that. So we're going to have a k hat direction. Oops, we don't need these vectors in here. Okay, so we have 2t squared times 12. Let's write that in black. 2t squared times 12 minus 8 times 3, t minus 5, all squared. And this is in the k hat direction. Okay, so now it's at the same instant, right? So that means that t is equal to 5 seconds. So let's plug in t equals 5 seconds. Right? Well, what does that give us? This term goes to 0 again. So that term goes away. So we're left with torque is equal to 24 times 25, right, in the k hat direction. That gives us a value of 600 joules, right, or Newton meters in the k hat direction. Okay, so next problem is DO2. We're given a merry-go-round, and initially a child is sitting at the center of the merry-go-round here, and this is given a rate, it makes 1 revolution every 5 seconds. We're asked to find what happens when this child walks out to the edge of the merry-go-round. What is the period for which this makes 1 revolution? Okay, so, well, we can find out some things about the system right away. We're told the radius is 2 meters. We're told that the moment of inertia of the merry-go-round itself is 500 kilograms meters squared. So just using that information, oh, and also that it makes 1 revolution every 5 seconds, right? So just using these informations here, we can just determine a few things before we really get started. So let's recall that that a rotational speed is 1 revolution 2 pi radians over some period of time. Well, we're told in this case that that period of time is 5 seconds, right? That gives us a rotational speed of, let's say it's approximately 1.267 radians per second, or we'll call it 1.3 radians per second. Okay, so in other words, omega naught, initial speed, 1.3 radians per second. Okay, well that's one thing we can figure out. Now what about the mass of the merry-go-round? I don't know if we'll need that necessarily, but we can still use it. We can still figure it out easily enough. So we're told that the moment of inertia is 500 kilograms meters squared. And for a disk, since this is essentially a disk, we can model it as a disk. The moment of inertia is going to be 1/2 mr squared. Well, that means this is 1/2 m, unknown, r squared. R is 2 meters, so that's 4, right? So that gives us 2m. So now m is equal to, this is just 500, take 2 to the other side, 500 over 2, 250 kilograms the units work out because this is meters squared, right? So this here was actually, this was 4 meters squared, and then we put it to 2 meters squared. We take 2 meters squared to the other side, we end up with the correct units. Okay, so now we have this information. We have this information. This is all just of the merry-go-round itself. We're also told that the mass of the child, let's give these subscripts. This is going to be mass of the merry-go-round, or the mass of the wheel. Well, we'll call it M1. That's the merry-go-round. M2, we'll call the child, is 25 kilograms. We're told that in the problem. A child of mass 25 kilograms walks from the center to the edge. Okay? And also we should note that the moment of inertia for a point particle on a disk, or let's just say a point particle rotating about an axis, is going to be mr squared, and that we can use for the child, right? So let's do, this was 1/2 mr squared, just to be clear. Let's put that here, right? So this is just an aside. We will probably use this information in a moment. Okay, so that's good. So we have a bunch of information about the system that we didn't necessarily have all in the same place before, right? So now we want to use this to figure out what is the final rotational speed, and thus how long does it take to make 1 revolution. So, well, recall we have conservation laws. We don't know, that we're told that this is frictionless, and that's fine, but we don't know exactly that this is going to conserve energy as this goes around and the child walks over here. So what we can do is we can use conservation of angular momentum. So angular momentum is equal to r cross p, right? That's r cross mv. And if we wrote this out here, we'd say this would be m v sine theta, and if we're talking about a very basic setup, we can just define theta to be 90 degrees, right? Because this is the angle between, if we remember from our torque conversations, that we have a velocity that's tangential to some rotating device, and then we have our position vector, right? So this would be r, and this would be v here, and the angle between them would be 90 degrees. in ideal conditions. Okay, so the point of me saying that is that we could just take R M V, right? That's going to give us R RM omega R, right? Because remember that V over R is equal to omega from before, so I just use that identity and plug this in. So now we have M R squared omega. And again, this is for a point particle. So really what this gives us here, this is just for an ideal condition of a point particle on the edge of a rotating something rotating, right? So we have this thing here with velocity v and position r. So really what this gives us is a moment of inertia times rotational speed. Now, this moment of inertia is going to change for different geometries, right? We have one for a disk that's different, and we have one for a cylinder. We have one for a solid cylinder versus a hollow cylinder. So what we want to use is just general form I omega. That's L. So we'll say L is equal to I omega. So now we can use this. We can say L initial angular momentum is equal to final angular momentum. Okay, so now let's set that up. So initially we just have the child is at the center and is not contributing to the angular momentum at all. It's just sitting there at r equals 0, right? We can still write that out in the equation. This thing is just spinning on its own. Then the child walks out. Now we have a point particle on the edge, and we have the rotational inertia of the disk itself. So what that means, initially, we have I1, right? 1 was for the disk, so I1 times initial speed. Okay? Then we have I1 final speed plus I2 final speed. So this is a really good starting point. Now what we are asked to find is the period of how long it takes to make one revolution. We know that the period is related to the final speed, so we just solve for the final speed. So that gives us omega f I1 plus I2 is equal to I1 omega naught. Omega f is equal to I1 omega naught I1 plus I2. So remember, I1 is the moment of inertia for the disk, and I1 is equal to 500 kilograms meters squared. Omega naught we found out was equal to about 1.3 radians per second. We figured that out earlier. I2, that's for the child, which we're modeling as a point particle on the edge of the disk, right? So it's just a point particle on the edge of the disk spinning around the axis. So that's mr squared. So I2 is equal to mr squared, and that's going to be equal to, we're told the child is 25 kilograms times r is 2 meters, so that's times 4, which equals I can write it, equals 100 kilograms meters squared. So that means that this is equal to 500. Oops, I don't know how that. Let's get rid of that. This is equal to 500 times 1.3, excuse me, over, we have 500 plus 6, 500 plus 100 is 600, so that's this. Okay. This is a value of 1.08 radians per second. We were at 1.3 radians per second initially. Right? When the child was here, this thing was spinning at 1.3 radians per second. Now that the child has walked out, we have decreased the speed to 1.08, so 1.1 radians per second. So not by much, but substantial enough. Okay? And I mean, recall that the mass of the merry-go-round is 10 times that of the mass of the child, so it didn't go down by much. If this child were super heavy, or if this were some other heavier object, we would probably have decreased quite a bit. Okay. So now let's relate this. Remember that omega is equal to 2 pi, which is 1 full revolution, over period. We want to know what the period is. So t is equal to 2 pi over 1.08 radians per second. This is radians, so that's going to give us a unit of seconds. And that's going to equal 5.82 seconds for 1 full revolution. So we've gone from, initially it was 5 seconds to make 1 complete revolution. Now it's almost 6 seconds to make 1 complete revolution. Again, that makes sense. Okay, so the next part of the problem says, is this process elastic? Is the kinetic energy the same when the child is at 0 and at r? Explain in detail. So, an elastic collision is one in which kinetic energy is conserved, and an inelastic collision is one in which kinetic energy is not conserved. Right, so what we're being asked to find is the difference in kinetic energy. If it's 0, that means it's elastic. If it's non-zero, it's inelastic. Okay, so what we do is we take, get that to work. Okay, if we can take the difference in the kinetic energy, right? So we have all the information we need to do that, because kinetic energy of a rotating object is going to be 1/2 moment of inertia times rotational speed squared. Right? So we can just plug in everything we know and see what the difference is. So, okay, so delta KE, kinetic energy final, is going to be the rotational speed. So we have 1/2 times I1 times rotational speed squared plus 1/2 I2 rotational speed squared of the final speed, right? Oops, minus, we're going to say 1/2, this is final, and this is going to be initial, 1/2 of the moment of inertia times rotational speed squared initial plus 0. There was nothing for the child initially. And what does this equal? So we can factor out 1/2, and then we just plug in for the rest. Then we have 500 times 1.3, oops, final was more like 1.08 squared, plus, remember this was 25 kilograms times r squared, which was 4, so that's 100, so that's 100 times 1.08 squared. I could have factored that out, but that's okay. Minus 500 for the wheel times the initial speed, 1.3, we'll call it 1.26. Let's be a little more careful here. Okay, and this gives us, so this actually gives us a change in kinetic energy of negative 46.98 joules. We say it's approximately 47 joules. We lost about 47 joules, right? Okay, and so where does this energy go? What happened? Well, if we can find our diagram somewhere. Here we go. So this child initially it was just the wheel spinning only, and it had some rotational speed that was higher than the final speed, right? So this thing is spinning, it's 250 kilograms, it's got a rotational speed of 1.3 radians per second. The child isn't really contributing to the system, but once this child walks out, the speed goes down, the mass increases, so our kinetic energy naturally does go down a little bit. But what happens? Well, this child actually needs to do some work in order to get out here. So it's not like this child just magically said, from here It wasn't here one instant and then here another. There was some exchange of energy as the child walks outwards towards the edge of the merry-go-round. So the child had to do some work on themselves. So child had to do work on their self, and thus on the system, to get out to the edge, right? To get to the edge. So that's, I think, as detailed as we can really get here. Next problem. Okay, we're given a solid cylinder of radius r and mass m, and it's able to pivot around a frictionless axle. The axle is pointed in the z-axis, which is pointing out of the diagram, and then there's a mass m that has a trajectory tangential to the cylinder. Okay, so the cylinder is free to rotate and is initially at rest. We are asked to consider. Okay, I just drew the diagram. So right, this is the solid cylinder rotating about this axis, which is pointing directly out of the screen. This thing is flying at this, and it's going to possibly collide just at the edge and cause it to spin. I'm guessing. Okay, we're asked to consider the angular momentum of the moving mass about the z-axis. So the moving mass is this thing. So what is the angular momentum with regard to this axis? Okay, well, angular momentum, remember, is r cross p, which is equal to r cross m times v. Right? Well, we know that this thing has some velocity v naught in the x hat direction. It's traveling in the x hat direction. Okay? Okay, the vector r has components in the x hat direction and in the y hat direction. Alright, so let's set this up. So what do we have? Let's do a cross product. We know some information about the system, at least enough to set this up. So we have r, the vector r, we have some x hat direction component. It's actually in the negative x hat direction. We'll just leave that. We'll leave that there. Oops, negative x hat, and then we have y hat component, right? Going upwards in the y hat direction. We have nothing in the z hat direction as far as we can tell from the diagram, and then so our angular momentum is, or our regular momentum p, is just mass times the velocity, and the velocity is simply in the x hat direction. So vx, so m times vx. This is 0, this is 0. So then we take the cross product, right? Recall this times this, these are both 0, and j direction, this is 0, this is 0. That gives you nothing. So now we just are left with k hat direction. That makes sense. That's what I would expect. And so we take this is 0, so there's nothing with regard to that component. And then we have this component here. So that's going to give us, this goes away, right? Minus, excuse me, minus m times vx times ry. And this is all in the k hat direction, recall. This is 0. So final answer, negative m v x r y k hat direction. And in terms of what we're given, vx is really just v naught, right? And we can consider that when this mass is here, this angular momentum is going to be the same, right? So we could just say that r is the radius of the cylinder. And so now we are going to end up with negative m, right? We have mass v naught r k hat. So that's the answer. If we consider the right-hand rule, we can think about, is this even, does this, what do we say, does it jive? Is it consistent with the right-hand rule? So what we have is we have, so we want to point our fingers in the direction of R, which is going to be straight up, right? That's R, and then cross P typically would be in the direction of your momentum, right? And so that's going to give you a positive k hat direction. This would be the thumb pointing straight up, right? This thumb pointing straight up. But now, since it's backwards, it's hard to show you. I can't show you my actual hand here. So since it's backwards, we go R, and then this is actually going the opposite direction, right? It's actually going this way. So that means that you're going to have a negative k hat direction pointing into the screen. So the direction makes sense, and given our options on the paper, I'd say E is the answer. Now it asks us to find the final angular velocity of the system after the collision. We're given a mass for the cylinder and a radius. Okay, so we're going to do a similar thing to what we did last time. We're going to use conservation of angular momentum, where the initial is equal to the final, right? So let's consider the initial angular momentum of the system. We're told that initially this thing is at rest. So the only thing in motion is this. So we're going to consider this angular momentum as the initial, and then we will figure out how, as this sticks together, right? And then we're going to figure out how fast these two things are moving together. So, all right. So I, omega, this is initial, we'll call this naught, 1 for the moving mass, is equal to I of the mass, omega final, plus I of the cylinder, omega final, right? So similarly, I mean, it's pretty much the same as what we did last time. So now omega final is equal to I1 over I1 plus I2 omega naught, where I1 is just going to be for a point particle, right? Because this thing flies at the cylinder and sticks to it on the edge, and then so now we have a point particle spinning around. So that's just going to be mr squared, right? We're told that the mass is 0.1 kilograms, and then the radius is 20 centimeters, so 0.2. And that's squared, okay? And the moment of inertia of the cylinder is going to be half mr squared, okay? I'm just getting this right off the worksheet. I haven't looked this up. I'm not sure how consistent that is. It must be the same if it's for a disk. Okay, so because a disk is essentially a small cylinder, so now we have 1/2 mr squared, and again we're told this is 1 kilogram, and this is 0.2 meters squared. Okay, before we plug all of that in, notice that we don't actually know the rotational speed of the particle. There might be some way to go through and find it, but really what's going on here, this is the angular momentum, and this is actually what we just solved for. We know what the angular momentum is. Okay, so now we have m times v naught, because we're given v naught, times r, and this is going to be, what did I say? This is half mr squared. Let's do this, m to r squared plus m1r squared. Okay, that's what we're looking at. So we do have all of this information. This is 0.1 kilograms. This is, we're told 6 meters per second. This is 0.2 meters. Right? This is all known as well. Half, same thing here. 1/2 times 1 times 0.2 squared plus 0.1 times 0.2 squared. All right, plug all that into a calculator. We get 5 radians per second. And that is option B. Just looking at units real quick. We don't really need to go through plugging in all of the units into something like this and canceling and solving, because right here, if we notice, we have angular speed, and on the other side we have an angular speed times moment of inertia times over moment of inertia over a moment of inertia. So this just gives us the units that we need. Next part of the problem, it says, which of the following physical quantities is constant during this process? And it gives us a bunch of options. Translational kinetic energy of the particle. Is that constant? Well, what happens here? Translational kinetic energy, the particle flies at this thing and then sticks. So now that we know that this is an inelastic collision, because this is in motion, this is at rest, now these two things collide and they're both in motion. That's an inelastic collision. We normally will lose some energy due to something like that. So A is not constant. Total mechanical energy of the system, again, same scenario, we're going to lose some energy. D says rotational kinetic energy of the cylinder. Well, we know that that's not constant because it starts from rest. So during this whole process, that is not constant. It's part C, net angular momentum around the z-axis of the cylinder and the particle. Well, that's exactly what we used to solve the problem, right? We used the fact that angular momentum is conserved in a system like this. And so, yeah, that's constant. So the answer is part C. So just put that somewhere. I'll put it down here. Part C. Angular momentum is constant. Next problem, page 387, problem 57. Okay, so we are given an angular momentum as a function of time, right? This is a function of time. Then it says, what is the net torque on the sphere as a function of time? So let's look at the relationships we have once again, as we like to do. Cross mv, which is your velocity vector, right, which is going to be r cross dr dt, right? Now, what is torque? We've done this, I think, earlier, I believe. This is going to be the same, similar relationship, but now we're looking at F. And F is going to be m times a. That's going to be times m d squared r dt squared, right? Well, looking at these relationships here, if L is equal to r cross m dr dt, and torque is r cross m d squared r dt squared, that means that the torque is going to be equal to another time derivative of L. And that's all we have to do, is take the derivative of this function. So let's do that. So t is equal to -3 times 4.59 t squared I hat plus minus 2 times 1.19 t j hat plus 6.26 k hat. So that equals -13.77 t squared I hat minus 2 times 1.19, 2.38 j hat plus 6.26 k hat. There you go, there's your answer. Thanks.